The microphone sitting on your desk right now and the microphone inside your phone are completely different technologies. Not just different brands, different physics, different materials, different reasons they exist. And yet most people treat them like they're all basically the same thing. Just a mic, right? Here is what almost nobody tells you. Over 90% of all microphones shipped in the world every single year are not the kind you see on YouTube desks or in recording studios. They are smaller than your fingernail. They are etched onto silicon chips using the same machines that make computer processors. And right now, there are probably 6 of them within arm's reach of you, even if you don't own a single real microphone. By the end of this video, you will know exactly what type of microphone is in every device you own, how each one works, why you would pick one over another, and why a technology declared dead in the 1970s is now on every major recording session in Nashville. No jargon, no lectures, just the actual explanation. Let's start with how microphones work at the most basic level, because once you understand the core idea, every type makes total sense. All microphones do one thing: they convert sound into electricity. Sound is just air pressure moving in waves. Your voice pushes air. That air pressure hits something inside the mic. That something moves. That movement gets turned into a changing electrical signal. The differences between mic types come down to what that something is and how the movement becomes electricity. That is the whole framework. Now let's walk through each type. The most familiar one, the kind at every concert, in every podcast studio, on every TV news set, is called a dynamic microphone. Dynamic mics run on electromagnetic induction. Here is what that means in plain terms. Inside a dynamic mic, there is a thin diaphragm, just a lightweight disc of material. That diaphragm is attached to a small coil of wire. That coil of wire sits inside a magnetic field created by a permanent magnet. When sound waves hit the diaphragm, it moves. The coil moves with it. A coil moving through a magnetic field generates electricity, the same principle behind every electrical generator ever built. What does that design give you? Toughness. Dynamic mics need no external power. They generate their own signal. They handle extreme loudness without distorting. The Shure SM57 handles 165 decibels before clipping, more than a jet engine at close range. The trade-off is sensitivity. Because the diaphragm has to physically move a coil of wire, it needs more force to produce a signal. Dynamic mics do not pick up subtle, quiet details the way other types do. Their frequency response typically rolls off somewhere around 15,000 Hz, so the very top end of the sound spectrum, the airiness and sparkle, gets softened. The Shure SM58 has been in continuous production since 1966, over 60 years. It is the default live vocal mic for basically every touring band on Earth. That is not tradition for its own sake. It is because the design genuinely fits what live performance needs. Loud environments, rough handling, no phantom power. Point it at a singer and it works. The SM7DB adds a built-in preamp, up to 28 decibels of gain on a switch. Michael Jackson's Thriller vocals ran through a variant of this capsule. One design, decades of use. The Electro Voice RE20 is the broadcast standard. Radio stations, news studios, broadcast booths. Variable D minimizes the proximity effect, the boomy bass that happens when you get too close to most mics. Announcers can lean in and the sound stays consistent. Now, condenser microphones. Same basic idea. Sound moves a diaphragm. Diaphragm movement creates electricity. But the physics inside is completely different. In a condenser mic, 2 parallel plates sit very close together. A rigid backplate and a flexible diaphragm. Together they form a capacitor. When sound waves flex the diaphragm, the gap between the plates changes, and the voltage changes. That changing voltage is your signal. The critical difference: condenser mics need external power to hold that electrical charge between the plates. That power is called phantom power, 48 volts of DC current running through the same cable as your audio signal. It is now standard on virtually every audio interface and mixer. You just see it as a button labeled 48 volts and press it before recording. What does the condenser design give you? Sensitivity. The diaphragm is extremely light, barely any mass to move. It responds to quiet sounds, high frequencies, and detail a dynamic mic rounds off. Condenser mics typically capture the full range of human hearing. 2 families exist within condensers: large diaphragm and small diaphragm. The size refers to the capsule, the actual disc that vibrates. Large diaphragm condensers have a diaphragm an inch or larger. That size adds warmth and a flattering quality to voices. These are the mics in vocal booths. The Rode NT1 has a self-noise rating of just 4 decibels. Most budget mics land at 15 to 25. That gap is audible in a treated room. The Neumann U87 at $3,600 remains the studio benchmark everything cheaper is measured against. Small diaphragm condensers, pencil mics, have a diaphragm under half an inch. The smaller capsule responds faster to quick transients and stays consistent off-axis. You see them on music stands in orchestras, over drum kits as overheads, and on acoustic instruments where precision matters more than warmth. Then there are ribbon microphones, and this is where the story gets genuinely surprising. A ribbon mic uses a different approach entirely. Instead of a diaphragm attached to a coil or 2 capacitor plates, a ribbon mic holds a single corrugated strip of aluminum suspended in a magnetic field. That ribbon, the entire transducer element, is 2 to 4 microns thick. A human hair runs 50 to 75 microns. The ribbon is thinner than that by a factor of more than 10. When sound waves hit the ribbon, it flexes. A conductor moving through a magnetic field generates electricity, same as the dynamic mic, same electromagnetic induction principle. But because the ribbon is exposed on both sides, it picks up sound equally from the front and the back while rejecting sound from the sides. That gives ribbon mics an inherent figure-8 polar pattern, which we will come back to in a moment. Ribbon mics sound warm, smooth, and slightly dark. They naturally roll off high frequencies. In the early days of radio and recording, through the 1950s and 1960s, ribbon mics were everywhere. Then the condenser got better and cheaper. Ribbons fell out of fashion. By the 1970s, most people assumed ribbon technology was finished. In 1998, Royer Labs introduced modern ribbon mics built to a durability vintage ribbons never had. The recording community rediscovered what ribbons do to guitar amps, brass, and strings, a quality no condenser replicates. Today, virtually every major recording session in Nashville has at least one ribbon mic in the room. One critical warning: classic passive ribbon mics and phantom power do not mix. If you accidentally send 48 volts through a vintage passive ribbon mic, you can instantly destroy the ribbon element. Modern active ribbon mics, like the Royer R122 volts, are specifically designed to accept phantom power because they carry active electronics inside. Know which type you have before you press that 48V button. Next, electret condensers. Pay attention here, because electret describes the majority of microphones you encounter in everyday consumer devices, even though it sounds technical. A condenser mic needs a charged capacitor to operate. In a standard condenser, phantom power holds that charge. An electret condenser uses a material with a permanent built-in charge. Think of it as a capacitor that never needs to be plugged in to stay charged. The charge is physically locked into the material itself. No external power needed for the core element. Many electrets do carry a small battery or low-voltage power for an internal amplifier circuit, but the transduction element is self-contained. That makes them small, cheap to manufacture, and easy to drop into compact devices. Your laptop's built-in microphone is almost certainly an electret. The lavalier mic clipped to a newscaster's lapel is an electret. The Sennheiser MKE2, a professional broadcast lavalier, is an electret condenser. Even the Neumann U87, that $3,600 studio benchmark, runs electret technology at its core. The range of quality in electret mics is enormous. A $2 capsule inside a pair of cheap earbuds and a $3,000 studio microphone can both technically be called electret condensers. The technology is not a shortcut, it is an architecture. What matters is how well it is executed. Now the type that accounts for over 90% of all microphones shipped worldwide. MEMS microphones, micro-electromechanical systems. MEMS microphones are not built in a factory the way traditional mics are. They are fabricated on silicon wafers using the same semiconductor manufacturing processes used to make computer chips. The microphone is literally etched into a silicon substrate at a microscopic scale. The entire package, diaphragm, backplate, and the amplifier chip bonded to it, fits in a space of about 2.5 millimeters by 3.5 millimeters, smaller than a single letter on this screen. The operating principle matches a condenser. A thin diaphragm moves relative to a backplate, changing capacitance, generating a signal. MEMS are made using chip fabrication, so they have something traditional mics do not: manufacturing consistency. Every MEMS mic in a batch sounds virtually identical. High-end condensers are still hand-matched at the factory because each one comes out slightly different. MEMS are not. Your phone has multiple MEMS microphones, not one. They work as a team through beamforming, comparing the signal at each mic to calculate which direction your voice is coming from, then isolating that direction and suppressing everything else. AirPods Pro 2nd generation carry 3 MEMS microphones per earbud, 6 total. One faces outward for noise cancellation, one faces inward to monitor what reaches your eardrum, a third faces the vent. All 3 run in a continuous feedback loop to sculpt what you hear. Most podcasters record with one. Smart speakers detect your voice from across the room while music plays through the same device. The MEMS microphone market alone was worth approximately $2.7 billion in 2024. Now let us talk about polar patterns, because the same microphone capsule can behave differently depending on how it is designed to receive sound. A polar pattern is a map of where a microphone is sensitive. Put the mic at the center of a circle. The pattern shows you where sound gets picked up and where it gets rejected. Cardioid is the most common pattern. Heart-shaped, picks up sound from the front, progressively less sensitive to the sides, and largely rejects sound from directly behind. The name comes from the Greek word for heart, cardia. Most podcasting mics, studio vocal mics, and live handheld mics are cardioid. One useful behavior: when you get very close to the capsule, bass frequencies boost. Engineers call this the proximity effect, and radio voices work it intentionally to sound fuller and more present. Supercardioid and hypercardioid are tighter, more focused versions of cardioid. They capture a narrower cone of sound in front. The trade-off: a small rear lobe appears, a spot directly behind the mic that it still picks up. Useful on loud stages where you need maximum rejection of monitor speakers, or in any environment with a lot of competing noise. Omnidirectional means equal sensitivity in all directions. No proximity effect, no rejection. Omni mics pick up the whole room, which sounds like a liability, but it is exactly what you want in certain situations. Lavalier mics are often omni because they sit on a lapel and cannot always point directly at the mouth. The mic needs to pick up whatever angle the speaker turns to. Omnidirectional also delivers the most natural, uncolored sound because no directional processing is shaping the frequency response. Figure 8, also called bidirectional, picks up equally from the front and the back while rejecting the sides. Ribbon mics carry this pattern inherently, because the ribbon strip is exposed on both faces. Figure 8 works well for 2-person interviews, where both speakers face each other across a single mic. Multi-pattern mics let you switch between patterns. The AKG C414 offers 9. The Blue Yeti has 4. One purchase, flexible setup. Finally, connections. Because the best microphone in the world is useless if you cannot plug it into what you have. XLR is the 3-pin connector for professional audio. It carries a balanced signal, 2 copies of the audio at opposite polarity, which cancels interference picked up along the cable. Run it over 100 feet with no noise. XLR mics need an audio interface or mixer, which lets you choose your own preamp separately from the mic. USB microphones have the audio interface built into the mic body itself. Plug into a computer, it shows up as an audio device. You record immediately. No separate interface required. For a single-person setup, a podcast, a voiceover session, a home recording, genuinely convenient. The Shure MV7 Plus, the Blue Yeti, the Rode NT USB Plus are all solid USB options in the $129 to $249 range. The limitation: running multiple USB mics on one computer gets complicated fast, because each mic has its own internal clock and they can drift against each other. 3.5mm connections are what you find on smartphone headset mics and small camera-mounted mics. Unbalanced signal, susceptible to interference over longer cable lengths but practical and widely compatible for run-and-gun video work. Wireless systems cut the cable with a radio transmitter. Professional UHF systems like Sennheiser and Shure have latency under 2 milliseconds, imperceptible. Consumer options like the Rode Wireless Pro and DJI Mic 2 run on 2.4 GHz, the same band as Wi-Fi, which is a trade-off but fine for most content creation. The global microphone market was worth $2.9 billion in 2024, projected to hit $5.8 billion by 2033. Over 90% of the units shipping right now are MEMS chips going into phones, earbuds, laptops, and smart speakers. The mics you see on YouTube desks are a fraction of what is actually out there. And yet every single type, the dynamic moving coil, the condenser capacitor, the ribbon, the electret, the MEMS chip, is doing the same fundamental job, converting air pressure into electricity. The differences come down to which physical mechanism does the converting, what that mechanism excels at, and what environment it was built for. The Shure SM58 at a concert tonight, the MEMS chip in the AirPods Pro, the ribbon mic in a Nashville studio. These are not competing technologies, they are solutions to different versions of the same problem. Now you know which solution is which. If you have a microphone question, which type should you buy? What the specs on your current mic actually mean? Or why your recordings sound the way they do? Drop it in the comments. I read them, and your question might become the next video. If this cleared things up, hit the like button and share it with someone who is about to buy their first microphone and has no idea where to start. Subscribe if you want to keep going, because next time we are getting into audio interfaces, what they actually do inside, why they matter more than most people realize, and how to pick the right one without spending more than you need to.